We're going to talk about springs in this video. Not just any spring, but the kind that follows what we call Hooke's law. Here's a Hooke's law spring, and I have placed a marker over here to show that the spring's original length or relaxed length. But since this real spring has mass, it's not exactly right to say the spring is relaxed, because the spring does get stretched slightly by its own weight. But in most problems in this course, we're going to treat the springs as massless unless otherwise specified or implied. So this marks our relaxed length. Here I have a 50-gram hook and a 50-gram weight for a total of 100 grams, 0.1 kilogram, with a 1 Newton mg. This 1 Newton stretches the spring to here. When I add one more 100 grams, the spring stretches to here. And if I add one more 100, guess how much it will stretch to? It'll be about here, right? And then one more 100 grams. About here. When I double the weight, the stretched amount doubles. When I triple the weight, the stretched amount triples. This is called Hooke's law. Not all springs behave this way. In fact, I had to go through lots of springs to find one like this. So you may ask, why do we study this kind of springs? Because for us beginners, these springs provide an easy model to deal with. Let's see. Right now, with the 400 grams hanging, the stretched amount is about 25 centimeters, or 0.25 meter. So we know that the force F pulling on the spring is proportional to the X, where the X is the stretched or compressed amount, because we can have a spring that can be stretched, or we can have a spring that can be compressed. Now let's plot a graph. That's force F versus the stretched amount X. Since F is proportional to X, so this graph should be a straight line. When there is no force pulling on the spring, the X is 0, so this straight line goes through the origin. And we measured that when the weight hanging is 400 grams, 0.4 kilograms, or an mg of 4 newtons, the stretched amount is 0.25 meters. So it goes through this point also. So the straight line goes through the origin, and it's like that. This straight line can likely extend until the force gets close to the spring's elastic limit. You know, if I pull on a spring too hard, the spring can become deformed permanently. In this course, we're going to stay within the linear range of the force, within the elastic limit. This means the force F is proportional to the stretched or compressed amount. And we can write force F equals to a constant times the X. And this constant, we use lowercase k for it. And this equation is what we call Hooke's law. And the k over here is what we call spring constant. Spring constant of a Hooke's law spring, or sometimes we call it a linear spring or an ideal spring. They all refer to the same kind of springs, the kind of springs that follow Hooke's law. Now let's find the spring constant of the spring we used for the demonstration. To find the spring constant, we can use the force divided by the stretched or compressed amount. We can also use our graph to find our spring constant. Which part of the graph will give you the K? The K is the slope of the graph. So if we find the slope of the graph, that's the spring constant. So either one, if we use slope, that's the rise over run. The rise will be the force 4. The run will be the total stretched amount, 0.25. So this will give us 16. What do you think is the unit for spring constant? Since this is 4 newtons divided by 0.25 meters, this gives us 16 newtons per meter, which is not the same as the Newton times meters. Newton times meters is force times the displacement, that's work, joules. The spring constant is Newton divided by meters, and it doesn't have a special name. So basically, the spring constant tells you that if we don't exceed the elastic limit and the linear range for the spring, then it will take 16 newtons to stretch that spring by 1 meter, which means that the spring constant tells us how stiff that spring is. The larger the spring constant, the more the force is required to stretch the spring or compress the spring a certain amount. So the K sometimes is also called the stiffness constant. Another thing is, for a spring that can be stretched, I will be pulling on the spring with this force, or pushing down on the spring for a compressible spring with the force. Now, my pushing force would equal to the spring constant times the compressed or stretched amount. So this spring gets stretched by a distance x, this one gets compressed by a distance x. When the spring gets stretched downward, my force goes downward. When the spring gets compressed downward, my force also goes downward. But if you're looking at this force of the spring, when you pull on the spring downward, the spring's force goes upward, opposite to the stretch direction. Same thing here. When the x goes down, the spring's force goes up. So the force and the x, if you're looking at the force of the spring, sometimes you see this equation with a negative sign because the force of the spring is opposite to the direction of x. And this negative sign here means this spring's force is a restoring force, because the spring's force is trying to push on the spring to make it go back to its original shape, or this one pulls back to make the spring go back to its original shape. Sometimes you see this equation with the negative sign, sometimes there's no negative sign. But in most situations in this course, we will just use the F equals to kx to use this equation to find the amount of the force. And sometimes it's possible when you see the force versus the stretched or compressed amount graph, it is the force of the spring, which means it's possible that you would see it plotted as F equals to negative kx, so the graph can be down there. And in that case, the slope is the negative k. Now let's see if the spring's force is conservative or not. We know that the work done by a conservative force does not depend on the path it takes. So let's do the test. If I stretch the spring from here to here, what kind of work would the spring's force do? Positive, negative, or zero? When I pull the spring down this way, the spring pulls on my hand upward. The spring's force goes upward while the displacement goes downward. The force and displacement, they are in the opposite directions. So the work done by the spring's force is negative. What if I go through a zigzag path like this one? I go down to here first, back up to here, and then down this way. What do you think? Let's see. When I pull the spring from here to here, the spring's force is upward when the displacement goes downward. Opposite directions, so the work done is negative. And then I move it back to here. Displacement goes up, the spring's force also goes up. Same direction, so the work done by the spring this time is positive. So the spring does positive work when I move it from here to here. And then I move it back down to here again. The spring would do negative work, which means for this part of the path, the spring's work cancels. It's zero. The net work done by the spring is zero. And then I go down again. For this part, negative work, which means the work done by the spring from here to here, up and then down, is exactly the same as the work done by the spring if I pull it straight down. So regardless of the path, the work done by the spring is the same. So the spring's force is a conservative force. We know that for every conservative force, we can define a potential energy for it. So let's derive a potential energy for the spring's force. We can use the idea of conservation of energy or the work energy theorem. The work energy theorem says that the work done by the non-conservative forces equals to the change in total mechanical energy, which is the change in kinetic energy plus the change in potential energy. If I pull with just enough force to overcome the spring's force, or push to compress the spring with just enough force to overcome the spring's force, that means the amount of my force equals to kx. And my force also is in the same direction as the x, so my force would equal to positive kx. Now if my force just overcomes the spring's force, that means there is no change in kinetic energy. Also, if the spring doesn't have mass, then there's no kinetic energy change either. There's no kinetic energy. So in this case, the non-conservative force that's doing work is the force from me. And the work I do is going to become the increase in the potential energy of the spring, which means my force does work, and that work turns into the potential energy stored in the spring. Because my force equals to kx, and it's a positive kx, so if I plot the force versus position graph, it would be a graph like this, the positive one. And if I have the force versus position graph, how do I find the work done by this force? That will be which part of the graph? Will be the area of the graph. So if I stretch the spring to a stretched amount x, that means the work would be the area of this triangle. So this will be the 1/2 height times the base. Of course, the base would be x. The height will be the force, which is kx. So we know the work done by me would be 1/2 kx squared to stretch the spring by a amount x, or to compress the spring by an amount x. When the spring is relaxed, we can say there is no energy stored in the spring, so the initial potential energy is 0. That means the final potential energy, the energy stored in the spring, or the PE stored in the spring, equals to 1/2 kx squared. We can call this spring's potential energy or elastic potential energy. So this is our new equation. So we have two new equations for a Hooke's law spring. The force is kx, and the potential energy stored in the spring is 1/2 kx squared. We will get some practice using them in the next few videos.